Hello and welcome to the lecture Optimizing CNN Part 2. In this lecture, we are going to discuss mainly two verticals. One is batch normalization and second is parameter initialization. In batch normalization, we are going to discuss what do we mean by internal covariate shift, what do we mean by feature scaling, how batch norm works, and how batch norm is beneficial for CNN. In parameter initialization, we start to define breaking symmetry, why symmetry is bad, that we are going to understand, and how parameter initialization helps to break the symmetry. So we start with batch normalization. By definition, batch normalization is a technique which has been used for training of a neural net to normalize the activation of a layer. So we have a stable scale and distribution. We will see that what exactly batch normalization do in this lecture. So why this batch normalization is required for a more robust, deeper network? That it reduces the internal covariate shift by stabilizing this activation of distribution, or you can say the activation distribution. It somewhat help in vanishing gradient problem. It allow higher learning rates, speed of convergence, and to some extent help regularization. So many things this batch normalization is. But before we start, we have to understand what is internal covariate shift. Now, please consider a situation where our network is very deep. That means number of hidden layers is substantially high. Now what happened? Each layer sees the inputs coming from the previous layer when the forward propagation is concerned. So input coming from the previous layer. Now what happening? During training, as we have seen in our earlier cases of backpropagation, the weight parameters of earlier layers keep changing. So the distribution of activation fed into layer or later layers keep changing too. I repeat it, that during training, parameters of earlier layers keep changing because of this weight updation thing. So the distribution of the activations fed into later layers keep also changing. Now then, if the input is changing, that the target is non-fixed. So this moving target is called internal covariate shift in deep learning literature. So since the input is changing, definitely the target is also changing, and that moving target creates this internal covariate shift. Now, what problem we suffer, or your deep learning model suffer? It constantly having to adapt a changing input distribution. So we have to adapt the input distribution are changing in this manner because of this weight adjustment in the backpropagation, and the later layers have to adapt this changing distribution. Okay. And why it is problematic? That means why it is hard to handle. If the input distribution of a layer keeps drifting, that means changing, optimization becomes harder. Definitely we have to use the smaller learning rates and training becomes slow and unstable, and deep nets become very much sensitive to the initialization. So those many problems happen. So in summary, every layer is chasing a target that is also not fixed. Then obviously convergence become very slow or somewhat very complicated. So this is basic concept is basically called internal covariate shift. Here we have to understand how our batch normalization going to handle this internal covariate shift. Now before we understand the batch normalization, first we have to understand how to normalize the thing. So feature scaling is a very simple method where we can understand min max normalization kind of thing. So what is our purpose? That given a set of data, that set of numeric data, we have to make this data between this fixed range 0 and 1. So what we'll generally do, this data, the particular data minus the minimum of this data by d max by d min. So if we do this d, then it will fix its range become whatever the numerical value initially it is coming in this range. So this is called min max normalization, min max normalization. Bit statistically, it's called standardization, zero mean unit variance. We consider data to zero mean and scales to the unit variance. So we need this d minus mean by variance. This d mu is the mean and the sigma is the standard deviation. So this is the way we normalize. Now take an example that's called feature scaling. It's also a kind of normalization. Consider our very old problem of house price prediction problem. Now two features we consider. One is house area, that is expressed in feet square, and it's range from 0 to 2000 square feet. And another is number of bedroom, what is come from 2 to 4 range. So they are clearly not in different scale. It's a 0 to 2000 and it is only 0 to 4 range, 2 to 4 range. Here we require to normalize in a certain range like how to do that? We use this size of feet by 2000, number of bedrooms by 4. If you do these two things, you can do it. Now here if you take the gradient descent, you can use the gradient descent for this. Without feature scaling, you can see that the path of convergence is much random. But with feature scaling, you can see that our path of convergence is very becomes straightforward. And this basically helps for a faster convergence. So gradient descent converges much faster with the feature scaling than without it. So this is a kind of example, very hypothetical and very simplistic example, how normalization helps. So in batch normalization, what we have to do, we have to normalize a scalar values within a batch or mini batch. So we first find the mean, that is the normal mean formula, that is we take a summation of all these m values and normalize it there, and we find the variance, the sigma b square by m di minus b square, and then we can find the normalized value of this di minus mu b by root over sigma square plus some errors, which is so this is the standard formulation that we mostly know, that how to normalize the values. Now let there is a neural net. Now this is layer 1, layer 2, layer 3 and layer 1, 2, 3. Now what we have to find out that how this values are flowing in the forward direction. That ZL is basically the intermediate value that is weighted of this WL of this LF layer, and inputs coming from the previous layer plus bias. That we know, it's very basic formulation. And then we put a kind of non-linearity over this zeta to get this AL. Now there is some confusion or contradictions that when we normalize, some school of thought said we normalize on ZL. Some school of thoughts basically says that normalize on AL. So it doesn't much matter whatever things we normalize. The idea is basically that we have to normalize A2 because if we think about this third layer, and we have to normalize this A2 to make this W3 and B3 much robust and stable the first term. So that is what we by doing this as normalization. Okay, so we can do this by normalizing Z2. Now you just think that given some intermediate values, this Z1, Z2, and Zn, this kind of thing, where this ZL is basically that we have said before that in this formula W of AL minus 1 is previous layer. Yeah. Okay. Now given these values, what we can do, we can find the mean of these zetas, and we can get some standard deviation or kind of variance. This and normalize this way. Now there is two important things. One is this gamma and this beta. These are two learnable parameters. Okay, that this gamma scales the normalized activation, and this beta shifts the normalized activation. So is the scale parameter, this scale parameter, and it is this formalization of this. Okay, so both are learned during this training. So this is this. So why this kind of normalization matters, as we have understood, this normalization stabilizes training because these activation values, these are the ZI values are being stabilized, and these sigma and beta preserve the model expressiveness. How robustness, expressiveness, a network can recover any required distribution. So in this way we can normalize easily. Okay. Now if we find this kind of algorithm here, so if we use this as algorithmic layout of this process, given the D over a mini match, input is this B1 to M. Parameters to be learned, this is gamma and this beta, and the output is Y, that's normalized. So we mini match means we can calculate in this way, we have seen before. Mini match variance we can find in this formulation, we have discussed before, and then we normalize in this way. And then we put the scale and shift parameter, that is the learnable parameter, so that we can learn this. So this is the somewhat very kind of pseudocode line thing of this mass normalization. Okay. Now here this is the forward propagation, and what we are going to do, that from given the x values, and we put wi and bi, this is the weight parameters, we get this linear output. Okay, that's zi. We put some batch normalization over zi, and we get this normalized zi. Then we put activation on this zi activation to get this ai, so that we can find out we get ai from this xi's. Again this ai fed to this to get this a2, that is going to find z2, then that's normal and puts this activation. Okay, So this way, this batch normalization is used. So that why this batch normalization is beneficial? So what it will do, since it normalizes, that reduce the internal covariate shift. So what is, we recall, what is internal covariate shift? It's a phenomenon where distribution of layers put changes during training. What benefit this BN achieve? The BN constraint activation to be approximately Gaussian. So then if we do this batch normalization, this activation, the distribution of the activations become Gaussian in nature. The normal, this kind of the standard normal. This stability, this will somewhat stable at least from the distribution viewpoint. Means later layers only need to adjust the changes in parameter, not the wild changes in distribution. That is the major improvement. That is improves the gradient flow, and it somehow helps the vanishing gradient problem to reduce the vanishing. So prevents activation from becoming too small vanishing or too large, because it range some range 0, 1, -1 to 1 or something. Because every activation is roughly normally distributed, the network propagates gradients more effectively through the deep layers. So without BN, this batch normalization, low activation of one layer can lead to the lower activation in the next layer, to the next layer, and so on. So ultimately we get this. But somehow it prevents, because it somehow put some sort of activation, so it becomes a range. And it's some sort of regularization, because statistics are computed in mini batches, some slight noise which can reduce the overfitting. So it actually improves the generalization. It's a kind of noise tolerance kind of thing. So by this way, the batch normalization helps. Now we start parameter initialization. So what does this mean? Parameter initialization means choosing the initial values of weights and biases in neural network before training starts. And the basic idea about this, we have to judicially choose these initial parameters before the training starts, so that we can get a robust and more, we can say, improved network. Now how this relates to deep network? As the depth increases, if there is a small error, the scales multiply, so it becomes large. If poor initialization is there, it causes vanishing gradient. At the same time, if we do the initialization very judiciously, then it keeps the signal magnitude stable and make the deep networks more trainable. That we understand this part of this lecture. Now, first of all, we have to understand what do we mean by the Baking symmetry. So, symmetry in the neural network is defined in this way. Let us consider a layer of multiple neurons, so 3 hidden. Now, if all neurons start with the same weights and bias, that means same parameter initialization. The parameters are initialized same values. What happened? They receive the same input. Then, if they got the same input, definitely they produce the same output. The error will be same. Error gradient will be the same during backpropagation. And they are updated exactly the same way for the weight updation. That we have discussed, that in forward propagation got the same input, we can get the same output, and get the same error, gradient, and when the back propagate, we can get the updated exactly the same way. So even when we have that the multiple neurons, they are all behave like on single neurons. This particular problem is called a symmetry problem in neural net. Now why this symmetry is bad? So why we really want that our neural network rely on different neurons learning different features. If this symmetry does not been broken, neurons become very much redundant. Similar thing they learned. So if this happened, then the expressive power of the net become very less. And even we add more neurons, there's no benefit at all because all are doing the similar kind of or some redundant learning redundant things. So network cannot learn this diverse representation. So this symmetry is not good for our deep learning things. Now consider a situation where we put the weights are initialized as all zeros. As we know that this is basically the kind of way A11 is W11 plus X1 to X2. A12 is coming in this way. W21 to X1 to X2. So what is H11? It is put some activation of A11 and some activation H12 is some activation of A12. Now what we have done? We initialized all W11, W12, W21, W22 all zeros. If we initialize it all zeros and we use the all neurons, the hidden layer 1 have the same activation, these are the same. Then what happened? A11 and A12 is 0 because these are zeros. These are the zeros. And H11, H12, since they are having the same activation, this is also 0. So this depending this way. And during this back propagation, what happened? This W11 is basically the weight updation. This is del of LW by del of Y to del of Y into H11, del of H11, del of H11, which is of del of A11 to etc. Using the chain. So what we see that this A11 is equal to A12 that we have seen. And this H11 is also, if we put it here in this two thing, then this H11 is same, these two are same, and these two are same, A12, these are again same, other things are already same. So this becomes two weight updations. So if the both weights are updated equally and remain equal, this way. So what happened if this is done? So weight becomes same, maybe the non-zero. It may be non-zero, but weight become after this maybe the non-zero, but the weights are becomes same if they are initialized to 0. And this symmetry will never break during the training. So even if we use the non-zero, but the same weight, same effect will also happen. Weights are initialized with same values, maybe not. This is called symmetry breaking problem. And this is what we have understood. It's not good for our deep learning. Now, what we can do to break this symmetry? So, the only property we can say, or what thing we can do, the initial parameter must be chosen to break the symmetry. Question is how we. If two hidden units have the same inputs and the same activation function, then they must have different initial parameters. Okay? Usually the best to initialize each unit to compute a different function, and this motivates us to the random initialization of the parameters. But how to initialize that matter, we can say random is not all zeros or not a particular number. Rather, it's a random initialization. Let's see how. Now, how parameter initialize break this symmetry? Now, if we get a random, even with a small random values, each neuron starts slightly different. Now, if it is different, it produces different outputs. Definitely, it will give the different error, so receives the different error gradients and learns different features. So, even if this kind of similar, but it learn differently, different features. Weights are always almost drawn from a Gaussian or uniform distribution. And so the scale of initial distribution does have a affect the outcome of optimization and ability to generalize. You can see one thing, larger initial weights will yield the stronger symmetry breaking effect and helping avoid redundancies. But too large is also not good, it may use exploding values. So what we understand that here that we have to choose the parameter or parameter initialization should do judiciously, so that we randomly taken some values for initial parameters so that we can achieve this. Now generally we say that weights drawn from the Gaussian, that weights are almost always drawn from a Gaussian uniform distribution. So it not that much matter. Choice of Gaussian or uniform does seems to matter much, but there may be some research is already going on. And the scale of initial distribution does have an effect on outcome of the optimization ability to generalize. So as we said, the larger initial weights will yield a stronger symmetry breaking effect, helping avoid redundancies. As too large is okay. But in case of biases, bias can be chosen constant. Zero initialization may also be okay. Okay, only the weights are initialized randomly, and extra parameters such as conditional variance or predictions are constant like biases. So, how parameter initialization help us? That bad initialization, as we say, that the symmetry is there, that causes the vanishing gradient, because the learning becomes very slow. That may cause the exploding gradient or symmetry. But the good initialization helps maintain the stable activation across layers, allow gradients to flow properly and speed up the convergence. So if we choose the initial, judiciously get it. So in this lecture, we are going to basically cover two topics. One is batch normalization and this parameter initialization. Basically discuss the internal covariate shift, feature scaling, how batch norm works, and why batch norm is beneficial in the batch normalization part, and what about breaking symmetry. Symmetry is bad, and how parameter initialization helps to break symmetry, discussed in this parameter initialization part. So we continue this lecture in part 3. Thank you.